Okay, so let's start today class. Today we are going to solve some problem based on the transformer efficiency. Okay. Or we maybe say that some mixed type of data given to you. That means for the efficiency and voltage regulation in open circuit and short circuit data. Okay, so you also find the efficiency and voltage regulation. So mixed type of problem we maybe say that, or we already discussed some separately that means for the open circuit short circuit problem and voltage regulation. Okay, so just try to see one problem if you consider yes is that a 10 kVA 2500 divided by 250 volt. Okay, so a 10 kVA 2500 divided by 250 volt. Okay, 250 volt single phase transformer, single phase transformer gives the following results. Give the following results. Open circuit test. Open circuit test. That means 250 volt. 250 volt. 0.8 ampere no load current. 0.8 ampere no load current. And 50 watts core loss. 50 watt core loss. Short circuit test given to you. Short circuit test data. Short circuit test data given to you. 60 volt. 60 volt. So, if you consider some mixed type of problem, that means data is provided of the open circuit and short circuit. So, open circuit data given to you 250 volt, 0.8 ampere, and 50 watts, and short circuit test data given to you 60 volt, 3 ampere, 45 watt. Okay, 45 watt. So, calculate the efficiency at various load. Calculate the efficiency at various load that means at 1 by 4, at 1 by 4, 1 by 2, 1 by 2, 1 1 and 5/4 and 5/4 of full load at 0.8 power factor of full load at 0.8 power factor at 0.8 power factor. Calculate the load kVA output in part B. Calculate the load kVA output, the load kVA output at which maximum efficiency occurs. At which maximum efficiency occurs. And also the value of maximum efficiency at 0.8 power factor. And yes. And also the value of maximum efficiency, the value of maximum efficiency at 0.8 power factor. At 0.8 power factor. And third one is your compute the voltage regulation and the secondary terminal voltage. Calculate the secondary terminal voltage. Calculate the voltage regulation and the secondary terminal voltage under rated load at and secondary terminal voltage under rated load at power factor under rated load at power factor at power factor 0.8 lagging and 0.8 leading. Okay, so 0.8 lagging and 0.8 leading power factor. 0.8 leading power factor. Okay. So how we can solve this problem? First of all, how we can solve this problem? So various data given to you, and first of all, in part A, you find the efficiency at the various loads. That means 1 by 4, 1 by 2, 1 and 5 by 4 of the full load at 0.8 power factor. Okay. And calculate the load KVA output at which the maximum efficiency occur, and also the value of maximum efficiency at 0.8 power factor. Okay. Third part is your voltage regulation and secondary terminal. So you may say that this type of problem is mixed type of problem. In one problem, you may find out various components, okay, various parameters of the transformer. So first you concentrate about the efficiency, part one. Okay, that means efficiency. So as we discussed in the previous class of the losses and the efficiency. Okay, so here given to you two losses test, that means open circuit test and short circuit test. So from the open circuit test, you find the core losses, and from the short circuit test, your ohmic losses at full load. Okay, as you know that open circuit test is performed at the low voltage side, and short circuit test performed at the high voltage side. And short circuit test performed at the 2 to 12% of the rated voltage, so that is given to you 60 volt, and you just find the rated current of the this side, high voltage side. Okay, so you know all the things how we can perform the open circuit test and short circuit test. So again, I'm not going to discuss for the same things. Just we require the core loss and ohmic losses from these two tests. Okay. First of all, you check this test is given at the rated current or not. If it is rated at the rated current, that is in full ohmic losses at the full load. Okay. And this voltage is low voltage side, that is given to you, that is 250 volts. So this loss is take place at the core loss. Okay. So just to concentrate about how we can solve this problem. And then you just put on the formula of efficiency, that means efficiency equal to 1 minus losses divided by output plus losses. Is it not? So solution of this problem is open circuit test has been conducted on the LV side, and you know that already. So open circuit test is circuit test has been conducted on has been conducted on LV side, LV side, or 250 volt during this test is calculated to the rated voltage on the LV side. Okay. 250 volt during this test is during this test is equal to the rated voltage on the LV side, is equal to the rated voltage on the LV side. Okay. LV side. This gives you, so just find out the rated current. Okay, so full load or rated current on the HV side, just calculate full load, or you maybe say that rated current, rated current on the LV side, on the HV side is equal to how much? That means this volt ampere divided by voltage, voltage of the HV side. So the voltage of the HV side is given to you 2500. So just divide 10,000 divided by 2500. Okay. So this current is equal to 10,000 equal to 10,000 divided by 2500. That means how much? 4 ampere. So rated current of the LV side is your 4 ampere. Okay, 4 ampere. But in problem given to you short circuit test, you know that short circuit test perform at the rated current. Sorry, rated current. Okay, so that's we consider the ohmic losses during the short circuit test. But these losses given to you ohmic losses at 3 ampere. So just calculate the ohmic losses at the rated load, that means full load current, that is nothing but 4 ampere. Okay, so full load ohmic losses is equal to 45 into 4 by 3 whole square. Okay, so full load ohmic losses equal to, let me calculate here, full load ohmic loss, that is represented by P suffix SC, short circuit test, or maybe ohmic loss. Okay, so ohmic loss means the short circuit is represented as SC, okay, equal to how much? 45 given at 3 ampere. So just find out at the 4 ampere. That means 45 into 4 by 3 whole square. Okay, 4 by 3 whole square, whole square. So this one becomes how much? 80 watt. Okay, whole square. That means 60 divided by 9. If you divide it by 45 by 9, then you will get equal to 5 into 16. That means 80 watt. So full load ohmic loss is your 80 watt. And you know that the core losses from the open circuit test, since this test is given data at the rated load of the LV side, so this one is at the core loss, that is nothing but 50 watt. Okay, so this one is your, so you already find out these two losses, that means ohmic losses at full load and the core losses. Okay, now you just find out the efficiency. Okay, so at 0.8 power factor and at 1 by 4 of the full load. Okay, so the core loss is same as the 50 watt. Okay, so at 0.8 power factor, and 1 by 4 full load current, full load, So the core loss is your how much? Core loss, that means PC represented by P suffix C equal to 50 watt. Core loss P suffix C equal to 50 watt. Okay. 50 watt. And ohmic losses is equal to how much? 1 by 4th of the full load, that means 80. Okay. So at 1 by 4 full load. So ohmic losses ohmic loss P short circuit equal to 1 by 4 whole to the power square. So 1 by 4 whole to the power 2 into 80 watt. Okay. So that is equal to how much? 1 by 16. That means 5. Okay. So 5 watt. Now just put on the formula of efficiency. So how we can write the efficiency equal to efficiency, that means represented by eta equal to 1 minus losses divided by output plus losses. Okay. So this one is equal to eta equal to 1 minus losses, that means core loss plus ohmic losses. So maybe represented as core loss, that means P suffix C plus ohmic loss at 1 by 4, that means how much? 1 by 4 whole to the power 2. So 1 by 4 whole to the power 2 into 80 into 80 divided by 1 by 4th kVA into cos theta. So cos theta is given to you 0.8. Let's put here 1 by 4 1 by 4 into how much? 10,000. The rating is your 10,000 into cos theta. Cos theta equal to 0.8. Just here 0.8. Okay. Plus this is your output plus losses, that means core loss plus ohmic loss at 1 by 4th of full load. So core loss, that means P suffix C plus 1 by 4th whole to the power 2, 1 by 4th whole to the power 2 into 80. Into 80. If you put the value of this one core loss, that is nothing but 50 watt, okay, then you will get the value of 1 minus 50 plus 50 plus this one how much? 5. Okay, so plus 5 divided by this one how much? 2000. So 2000 plus 50 plus 5. Okay, that means 55 divided by 2055. Okay, so 55 divided by 2055. Okay. If you divide this one, you will get the value of 55 divided by 55 divided by 2055. You will get how much? Okay, so this one is your 1 minus this one, na? So this one is your 1 minus this one. That means 2000 divided by 2055. Okay, so 2000 divided by 2055 equal to how much? 2000 divided by 2055. So 97, that means 0.9732. Okay. That means 97%. Since is your 97.32%. Okay. Similarly, you may find out at the other load. Okay. That means at 1 by 2. If you find out 1 by 2, so here becomes 1 by 2 in place of 1 by 4, is not. So when you find out the efficiency at 1 by 2 of the full load, so at 1 by 2 of full load current, full load current. So just write here efficiency equal to just here eta equal to 1 minus losses divided by output plus losses. So losses it becomes core losses is same. So 55, sorry 50 plus This one becomes 1 by 2 whole square. One by 2 to the power 2 into 80. Okay. Divided by 1 by 2 into 10,000 by 2 1 by 2 into 10,000 into cos theta equal to just put 0.9, 0.8. So into 10,000 into 0.8 into 0.8 plus 50 plus 1 by 2 all to the power 2 1 by maybe written as 1 by 4. Okay, so 1 by 4 into 80. So if you simplify this equation, you will get the value of almost equal to how much? 1 minus this one 4, that means 20. So 50 plus 20 is your 70. 70 divided by this one, how much? If you multiply 10,000 into 0.8, so it will becomes how much? 8,000. 8,000 divided by 2, that means 4,000. Okay, so 4,000 plus 70 plus 70, that means 4,000 divided by 4,070. 4,000 divided by 4,070. 70 equal to almost equal to 98.28%. Okay, 98.28%. So maybe solve for the other two parts, that means I had to rated full load, rated or full load, or another is your how much other load is your 1 by 5 by 4. Okay, so just simply put here the formula and just calculate the efficiency at other two parts. Okay, if we just calculate for the part B, okay, that means for part B, so let the maximum